let us utilize once again the hypothetical reaction A and B forming C and D. And we want to determine again the rate of the reaction. And in order for us to do that, we have to find an equation that will give us basically the rate of the reaction. And that is what we call the rate law. Okay. Now, the rate law can be calculated based on the concentration of the reactants. So generally, if you're going to utilize our hypothetical equation right here, the rate law is expressed as R equals K times the concentration of A raised to alpha times the concentration of B raised to beta. So what is alpha and beta? Alpha and beta, these are what we call orders of the reaction in A and in B respectively. Now K is what we call our reaction constant. So if you want to determine the overall order of the reaction, you simply have to add alpha and beta. Again, we are utilizing our hypothetical reaction here. So if you have another third reactant, then you have to include its order of the reaction in that particular reactant and add to this equation for the overall order. So for example, if the reaction is first order in A, then our rate law expression will be R equals K times CA. And take note that CA has 1 as its exponent kasi nga first order in A. Okay, ibig sabihin alpha equals 1. Now, what if we have a case wherein it's first order in A and first order in B, right? And that means that overall, we have a second order reaction. So what will be the expression for the rate law? So we will have R is equal to K, CA, CB. Kasi first order in A, so the exponent will be 1. First order in B, so the exponent will be 1. And if you just add alpha and beta, 1 plus 1 equals 2. So therefore, second order overall siya. What if we only have a case wherein it's just second order in A alone? So if that's the case, then the rate law expression will be R equals K CA squared. And finally, if we have a zero order reaction, then that means R is just equal to the rate constant. However, in many types of reactions, like in gas phase reactions and even in biological reactions, the values for alpha and beta are not really whole numbers, so they could be in fractional form, and the rate law expression can assume other forms, not just the ones that we are discussing about. We'll get to that later. But for now, the problem will arise such that we want to determine the rate law expression experimentally. So how do we do that? Now, we have this what we call the initial rate method, wherein experimentally we can actually determine the concentrations of the reactants and determine the initial rate. So we can measure them, right? Now, let's say that the initial rate can be expressed as R0, okay, equals K prime times the concentration initial of a certain reactant A raised to alpha because it is the order of the reaction. So what we can do for this expression is we take the logarithm of both sides of the equation, of course. So that will be log of the rate equals log of k prime plus alpha log of the initial concentration of the reactant. Now, if you notice, we have linearized the equation, and therefore, if we're going to plot um, the log of the initial concentration of the reactant in your x-axis and the log of your initial rate in your y-axis, you will get alpha as the slope of the line. Okay? So for example, I want to determine the rate law expression, or maybe just the order of the reaction for this particular biochemical reaction. So we have glucose acted upon by an enzyme forming your products. And you're given here the data, the initial glucose concentration. So probably it's in terms of millimoles per liter. And your rate is also given, maybe millimoles per liter second. So I wasn't able to affix the proper units. So how do we do that? Let's say that the enzyme concentration, okay, the concentration of the enzyme is equal to 1.34 millimoles per cubic decimeter, and let's assume this to be constant. Okay, so I want to find the rate law expression for that reaction. So that will be K times the concentration of glucose raised to alpha times the concentration of the enzyme raised to beta. Okay, now if I said that the concentration of the enzyme is constant, okay, I can merge this constant with the constant K, which is our reaction constant. So in that case, the expression can be simplified as R naught or R sub 0 equals K prime times C, or the concentration of glucose raised to alpha. So this is now our simplified rate law expression pending the determination of the order of the reaction alpha. Okay? And you can do this for cases wherein the other reactant is constant, such as for example, if you have a solvent, okay, wherein it's in larger amounts, which is constant, so we can merge that into the rate law, or into the rate constant K. So if we now take the log of this equation, we'll get log R is equal to log K plus alpha log of the glucose concentration. So we can plot the log of the glucose concentration in the x-axis and the log of the initial rate in the y-axis. And here I did it using Excel. So I made some inputs. So we have the glucose concentration and the initial rate. So I took the log of both the glucose concentration and the, no, this is not the enzyme concentration. So this should be the R naught, log of the R naught. Anyway, once you have done that, you can plot it using Excel, and you will be able to determine that the relation is fairly linear with an R squared value of 0.9999, so close to unity. And you have there the equation of the line. So therefore, we were able to determine the slope, which is now equal to alpha, is 0.9986, which is fairly close to 1.0. So therefore, this is now the order of the reaction. And the rate law expression, therefore, will be R equals K prime C glucose, or the concentration of glucose, raised to 1. And there are other calculations that you can do here. You can actually determine the value of K because you have K prime and the concentration of the enzyme is given naman. But anyway, this is now our rate law expression. The order of the reaction is equal to 1.0.